Okay, this is section 2.5, the last section here for week 2, and we're going to be talking about the zeros of polynomial functions in a little bit more depth here with a couple other theorems that are useful to us. So these are learning objectives again. Make sure you read the e-text, and these are the examples I want to go over, plus some more explanation that might help you when you're reading through the e-text. Okay, so first of all, the rational zero theorem. That says that the possible rational zeros, rational means a fraction, right? Ratio. So the possible rational zeros of a polynomial are the following. You take all the factors of the constant term at the end of the polynomial, divide it by all the factors of the leading coefficient term, okay, of the leading coefficient itself. So when I look at this first example, I have a fourth degree polynomial. So my highest power is 4 for x from x to the fourth. My constant term is minus 4. So my possible rational zeros are, look at all the different factors of minus 4. So that's plus or minus 1, plus or minus 2, and plus or minus 4. Divide that by all the possible factors of the coefficient of the highest power of x, which is 5. So those are plus or minus 1 and plus or minus 5. So I take every term up here, divide it by every term down here, and I can see that all my possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4, then plus or minus 1/5, plus or minus 2/5, and plus or minus 4/5. Okay, so those are all my possible rational zeros. I would have to then go and check until I found one. And then I could use, I could use synthetic division to do that, or just check it, by plugging it in. So let's extend that idea and actually find one. So example 2, 6x cubed minus 11x squared minus x plus 6 equals 0. So I have a cubic equation set equal to 0. Cubic polynomial set equal to 0, so it's called a cubic equation. And then I want to list the possible rational roots. So it's all of the factors of the constant term. So all of the factors of 6, which is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Divided by all of the factors of the leading coefficient, the coefficient of the highest power of x, so 6 here. Again, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And when you look at all the different combinations of those, take the 1, divide it by all those, take the 2, plus or minus 2, divided by all those, plus or minus 3, divided by plus or minus 6, divided by all those, and these are all the different possible ones. All right. So then we want to test them. Well, we hope we find one pretty quick because that's a lot to test. So I'm going to test x equals 1. And I cheated a little bit. I knew that would work. But how do I test x equals 1? I use synthetic division and see if I get a remainder of 0. As soon as I get a remainder of 0, I know I have found one, right? Because that's like plugging in 1 when I do that. We just learned that from the remainder theorem. So when I do synthetic division for x equals 1, it works out. I get a remainder of 0. And woof, we found x equals 1 already. That means a factor of that polynomial, 6x cubed minus 11x squared minus x plus 6, a factor is x minus 1 because x equals 1 is a root. So, and the quadratic I'm left over with has these coefficients. So that's 6x squared minus 5x minus 6 right here. So you might stare at that for a while and see if you can factor it. You'll quickly, hopefully, be able to realize I can't factor it, so I need to use the quadratic formula. Hopefully everyone's familiar with the quadratic formula. Take a look, make sure you understand all those pieces. And thus I get two different roots, 15/12 plus or minus 13/12. So 18/12 or minus 8/12, which is 3/2 or minus 2/3. So these are my three roots. All right. The properties of the roots of polynomial equations. A polynomial of degree n has n roots. It will always have n roots, counting multiple roots separately. So if it has a multiplicity of 3, that would be like 3 roots, even though it only looks like 1. Imaginary roots always have to occur in conjugate pairs. That comes from the quadratic formula where it's plus or minus this guy, which would be, if it's negative, you're going to get imaginary roots that are in conjugate pairs. Okay? So how do we use that? If we want to find the nth degree polynomial where I have some information, I'm told that n is 4, so I'm going to have x to the 4th be my highest power that I see for x. I'm told that I have minus 3, 1/4, and 2i are zeros. Now a fourth degree polynomial will have 4, but even though they only told you 3, they actually told you 4 because if 2i is a 0, so is minus 2i, its conjugate. Okay, so that means that all the factors would be x plus 3 to get x equals minus 3 as a root, x minus a fourth to get x equals 1/4 as a root, x minus 2i to have 2i be a root, and x plus 2i to have minus 2i be a root. So then I could multiply all that out and I'd see what the polynomial is. The only thing I wouldn't see is what's the coefficient of the leading term. So you needed this other piece of information, f of minus 2 equals minus 144. Okay, so when you plug that in, you would get, oh geez, I plugged in 2. So pretend this was 2. F of 2 equals 100 minus 144. I plugged in 2. Change this to a positive 2 on your notes. F of 2, when I plug that in, I would see that A4 is minus 144 over 70, right? You know that F of 2 is minus 144. Plug it into each one of these factors, you get that. So A4 has to be this guy. Plug that in, and there's my fourth degree polynomial. The last thing from this section is Descartes' rule of signs. It simply says that however many changes of signs I see will tell me what the positive number of the possible number of positive real zeros is the number of changes of sign I see in my polynomial. So here's my polynomial where it changes from minus to positive, from positive to minus, then minus to positive again. Here's positive to positive, so no change. So this had 3 changes in sign. That means that the number of positive real zeros could be 3, or you go down decreasing by 2. So it's 3 or 1. If I take f of minus x, see what that is by plugging minus x in here. Now I look at the changes of sign in f of minus x, I only see that there's 1 change of sign. When I go from minus to positive here, that means the possible number of negative real zeros is 1.